Okay, good morning. Let's jump right in. We have a lot on our plate, and I need to get you everything you need to do the homework. For some of you managed already, but I understand we got a little bit behind in the lecture, so we need to make up for that. All right, so we started talking about circuit components. We talked about sources. We talked about resistors, and this is a circuit with a few resistors. Actually, the circuit on the left has 3 resistors, and we can replace it with just 1 resistor if we choose the value of this 1 resistor or EQ correctly. And how would you choose it? What's the right value for our EQ if we want both circuits to behave just the same? Right, it's a sum, so that's so easy. It's almost hard to answer. It's almost embarrassing, right? So obviously, hey, you need to know that, right? And now we will get over a bunch of things that you just need to know in order to reasonably and quickly operate with circuits. All right, why is that the case? Well, it's the case because of course it's the case of Kirchhoff's laws and Ohm's law, but really, but we can boil this down to in this situation that the resistance of several resistors simply adds up if these resistors are in series. Why are they in series? Well, it's because the current through all of them is the same. Okay? So series connection, important to recognize. If we have resistors, for example, connected in series, we simply can add them all up and replace them with 1 single resistor. Obviously, that's very important because as our circuit diagrams get more and more complicated, it's important to be able to reduce them to what actually matters. Otherwise, we get confused. All right, so series connection, well, obviously there is a dual to it. That's the parallel connection. So here, again, 3 resistors. Could have been 5 or 7 or 2. In here, they are in parallel. What does that mean in parallel? Well, the voltage across each of these resistors, how would you verify that? Well, Kirchhoff's voltage law. The voltage across each of these resistors is the same. V1, I call it here. I could have flipped V1 upside down. Several people of you asked me in the office, how sure, when I draw up the circuit, I can put my arrows and so however I want, but then afterwards I have to be consistent. I have to, for example, put it the same over there. Right. All right, so how could you choose the resistor or EQ so that both situations are the same? Well, we can write an equation for I1. I1 is equal to the current flowing through resistor R1. Well, what would that be? So if we know the voltage across resistor R1, what is it? We just gave it the name V1, right? And we know the value of the resistor. Well, then the current is the ratio of the two. Okay, so I1 is equal to V1 divided by R1. And then, of course, there is also current flowing through R2 and R3. So V1 over R2 and V1 over R3. I guess many of you have read this already in the book. And I1, of course, is also equal, if we look at the circuit on the right side, equal to V1 over Req. And from here we can see that 1 over Req is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Okay? Okay, fine. So it's a little bit more inconvenient than the series connection because we have to add up all these fractions, but at least that's correct. Now, very often we will use a different notation for that. That's really the mathematically correct thing is add up all these fractions, but very often because it's so clumsy to write, we will actually write our EQ, and remember that also because it will save you a lot of handwriting, is equal to R1 parallel with R2 parallel with R3. Okay? That's just the shorthand, and then we know what we really mean is this up here, but this is easier to write. Okay? That's all there is to it. Now, one more trick. Writing all these equations, fractions and calculating these fractions, a pain in the neck, so we can avoid that by simply defining another element, a conductor, and and the conductor says how much it likes to pass current. Right? The resistor basically says, how much do I resist current flow? The conductor says, how much do I like to let the current through? So conductance is simply defined as 1 over resistance. So if I give you a resistor that has 1 k ohm, you easily can figure out how to represent that same resistor as a conductor, and the value of that conductor would be 1 over R, 1 over 1 k ohm, so 0.001, 1 over ohm, and 1 over ohm, the unit has names. Siemens is one name, that's the easiest one to write. Some people write ohm the other way around, and some people put the omega upside down. They're all fine. Choose the symbol that you like best, or that makes you smile. Okay, so anyways, there we have sort of a funny thing that 2 different units are actually equivalent, right? Well, maybe the equal sign is a little bit risky there. If you just replaced 1 k ohm with 1 millisiemens in an equation, that wouldn't be quite right. But it corresponds to. The equal sign here just means corresponds to. Okay? So what's the good thing about that? Well, now we can again write what. So Ohm's law now looks like this, right? The voltage is equal resistance times current. That's on the right side, the normal Ohm's law. And well, if we replace R with 1 over G, then we can say the current is equal to conductance, G, times voltage. You have a question? Why is it yeah, it's not really equal. It corresponds to. I'll need to change my slide. I do this usually at night, and late at night you take shortcuts, and they are not always quite right. Okay, so beware. That funny sign there means corresponds to. All right, so conductance. So we can again write our equations. Here, I1 is equal to, well, G1, and now I'm using this relation, G1 times V1 plus G2 times V1 plus G3 times V1, and then it's also equal to GEQ times V1, where V1, of course, is the voltage across here. Okay? And so out of that we see, well, I already wrote it down here. Out of that we get G equivalent equals the sum of all the individual conductances. There's really nothing new, it's just a more convenient way to write things. And actually very often when I have circuits where there are lots of things in parallel, I actually will, even though if I go to the shop and I want to buy a resistor, I have to tell them how many k ohms I want or whatnot. I can then, of course, on my schematic, I can, instead of writing 1 kilo ohm, I can write 1 millisiemens, and then afterwards I get a little bit simpler equations that have your fractions. Okay? All right, well, now we are ready to do our first little sort of practical example. Let's suppose that we designed a cook stove. I know that's not high tech, but we got to start somewhere, right? All right, so we have a cook stove. What actually is a cook stove, an electric cook stove? Just a bunch of resistors. Well, in a cabinet, right? Bunch of resistors. Why? Well, because if we pass a current through a resistor, it dissipates power, and what happens to that power? Well, it becomes heat, and that heats our eggs in the morning. Okay? So now another feature of stoves, of course, is also that we can regulate how much heat it produces, because depending on what we cook, we need more or less. Okay, so how do we do that? Well, we simply switch in different resistances. So now here I actually represented, in this example, the resistances or heating elements. I represent them as conductors. So there are 2 conductors available to us in this particular stove. One of them has a 1 Siemens conductance, so it actually has a resistance of how much? 1 ohm, right? And the other one has 2 Siemens conductance. The resistance would be half an ohm, right? So we have these available, and then to the left side is the stove. We plug it into 100 volts. I wanted simple numbers, that's not necessarily realistic. And so So that element G there can be replaced by one or a combination of the two elements G1 and G2. And the switch that you have on the stove, really, all it does is it chooses the right elements and puts them in the right configuration. That's really how the stove operates. Okay? So, here we already say, well, power is equal to voltage times current. Well, we remember that. Well, what's the current? Voltage times, well, what's the current? Voltage over resistance, or voltage times conductance. So that's V1 squared times G. Okay, so now, how are we going to switch in the different elements, G1 and G2? Well, first of all, we could just say, well, we switch in element G1, let's say, okay? So then what we really do is we replace this element G, we replace it just with G1, right? That's what our switches do somehow on the stove, right? Well, you figure out how to arrange the switches. So now, if we had the conductance G1 substituted for that G, then we would get the power delivered to the stove, so that would be PG1. If we have the only element we had there was G1, would be PG1. That would be V1 squared times, well, G1, that's 1 Siemens. Okay, so then we have 100 volt squared, that's 10,000, right? Times 1 is 10 K. K what? K watt, right? Okay, so if we simply put in that element G1, then we get the power delivered to our stove is 10 kilowatts. We could, of course, do exactly the same thing. We could take the element, we could remove the element G1 and take instead the heating element G2, and then very similar, we would get 20 kilowatts. Is that all we can do? Okay, we could do it in parallel. So then we have P G1 in parallel with G2 is equal to V1 squared times G1 plus G2, right? And that's equal to 30 kilowatts. And then what's the fourth combination in series? So then it's G1 V1 squared times, okay, right, so actually we had 1 ohm and half an ohm, so 1 point, and that's something like 6.7 kilowatts, okay? So simply by arranging these heating elements in different ways, series, parallel, and using individual ones, we can sort of sweep the power of our stove up from about 7 kilowatts to all the way up to 30. Okay? Make sense? Any questions? You look a little puzzled. I don't know whether it's just you're puzzled that I make such a simple example, or yeah.
How do you adjust the spirals? And they the resistors in the circuit?
Yes, these spirals actually would be the resistors. The resistors are actually in the spirals inside.
How do you adjust or replace the spirals?
How do you replace them?
You just change the current passing through them.
Well, actually, you know, I haven't taken apart our stove or so. I'm not sure how they do that. So certainly the simplest way to do that is that you have a number of separate loops, wire loops or resistor heating element loops inside that spiral, and then you have several prongs that connect to them, and you wire them out to your switch, right? You could also build such a stove differently. There are lots of, with fancier electronics, you could actually modulate the voltage across or the current through them and so on, but that requires circuits that we haven't talked about, because you wouldn't, for example, want to put another resistor somewhere that takes up the rest of the heat, right, if you want to drop the voltage or so, because then somewhere else in your stove would get blazingly hot, and hey, that wouldn't be very good, right? Okay, so this is a way certainly that we could make such a stove, and I'm sure simple ones are actually built just this way. Okay, so more simple circuits. Another one. Oh no, this is an example, right? Sorry. So here is an example, right? We have a circuit. These circuits really they will show up in our circuit diagrams here and there, and we just need to sort of be able to deal with them. So here we have both series and parallel connections, and we want to reduce this to that simple circuit there. So how would you do that? Well, you have to go a little bit in sequence here. You have to recognize first, is there any series or parallel connection that I can reduce? Do you see any? Yeah, R1 and R2, they are in series, so we can reduce those to, you can reduce the circuit to just R4, and here we have R3, and here we have to introduce some nomenclature. I make this, well, R1 and R2. Huh? Okay? Because they're in series, they simply add up. Now, what's the next thing we can simplify here? Okay, these are in parallel, so we can write R4. And so we have R1 plus R2 in parallel with R3. Okay? And then finally, this whole thing is in series, and from there we get, I'm not going to even draw it anymore, well, it's drawn up there. Our EQ is apparently equal to R4 plus R3 in parallel with R12, where R12 really stands for R1 plus R2. Okay? And you know what R3 parallel with R12 means. It means that you have to take the reciprocals of each of these, you have to add them up, and then you have to take the inverse once more. Then you have this. Now you're asleep, huh? Okay, so I guess we need to go a little bit faster, otherwise some of you will not be able to quite be with us for the whole thing. All right, so well, let's actually skip this. Let's move on to something more. So here is another very simple circuit that we'll find all the time in circuit diagrams. And in fact, we're going to use it in our design examples very shortly. It's very useful. It's called a voltage divider. So we're now here, we're kind of in that mode where we are learning the vocabulary of a new language, right? So it's simple stuff, but we really need to know this, and we'll use it a lot. So so here we have two resistors. In which configuration are they? They're in series, right? So what's the current actually flowing through them? Well, I1 is equal to Vs over R1 plus R2, right? Because they are in series. So, for example, it would be 7K ohm here. Now, what is the voltage V1? Yeah. So the voltage V1, use Ohm's law, right, is R1 times, well, the current is I1 because the current through all the elements here is the same. They're all in series, okay? So we get actually V1 is equal to Vs times R1 over R1 plus R2. This is terribly simple, and it's terribly important for here. For this class. This you just need to know. You need to be able to see, oh, these two resistors are in series. If I can figure out the current, I can figure out the voltage across one of them. Okay? You can learn this equation by heart if you like, or alternatively you can, and that's probably better, you can just learn how we construct this equation. Okay? But you need to know this. If it takes you 5 minutes to figure this out, you understood it, but you're not going to do well as a circuit designer, and you're not going to do well in EE40. So you need to be very, very familiar with this. Much like the word vocabulary in a language, you just got to know it. Okay? So there is a dual to the voltage divider. You also can set up a current divider. So here we have a current source I1, and then we have a whole bunch of currents, and the question is, what is the current through any particular one of these resistors? Okay? So how are we going to do this? Well, we can first figure out the voltage. The voltage across here, let's call this voltage here V1. Voltage V1 would be equal to I1 times what resistance? Right, the resistance of all of these in parallel. So that would be R1 parallel, R2 parallel, R3 parallel, R4. Again, how would we figure out what actually this funny thing is? If we wanted to calculate that, we would take the reciprocal of every interval, all of them, add that up, and then take the reciprocal again. Okay? That's how we do it. Alternatively, we could first switch to conductances and then divide by the conductance. Add them up and divide by the conductance. Okay, so I2 is now equal to V1 over R2. Okay, Ohm's law again. Ohm's law obviously is something, hey, you got to know that. And so we can finally write I2 is equal to I1 over R2 times R1 in parallel R4. Okay? Again, a situation that occurs very frequently, and we need to know how to recognize it and how to analyze it. I don't know this equation by heart. Okay? I will derive it every time, but I can derive it in the blink of a second. Okay, so, well, interesting. Actually, not that interesting, right? But now, let's do something that is a little bit more interesting. Let's use all this stuff for something. So, if you look at the power brick for your laptop, it will be something like 20 volts or 15 volts or so. But of course, on your laptop internally, it doesn't work off 20 volts, right? The CPU uses give or take a volt or so. And so what you really need is inside the computer, you need a way to step down from the higher voltage to the voltage that the particular component needs. So here I made a simple example, go down from 18 volts to 3 volts. Incidentally, why does the power brick supply 18 volts and not just 1 volt or so? What would happen if you made the power brick just 1 volt? Yeah.
It's a lot easier to step voltage down than up. So
that's maybe that's actually some of the reason, but it's not the main one. There's something. Yes. Exactly. We need a lot of amps. And why is that bad if we would need a lot of amps? Exactly. You need a really thick wire. So instead of having that nice thin and flexible cable, you would have a cable that is like this that you connect to your laptop. Mess, right? So that's the main reason. The reason you mentioned is also true. Okay? So so the situation that we have is here we have a power brick. And notice now we are already totally attuned with the thing. We're not going to draw a power brick or something like that. Power brick really acts like a voltage source. Close enough to an ideal voltage source, so that's the symbol we use here. And then over there we have a load, that's some part of your computer. Right? We're not interested in the details what that is. We're not going to draw a billion transistors here. Gee, it wouldn't even fit on the screen, right? But we'll simply say, well, here is some kind of a component that needs 3 volts. That's good enough, right? So on the circuit diagram, that's all that matters, so that's what we put down. Now here we need your clever circuit that somehow miraculously takes 18 volts and out comes 3 volts. How could you do this? Any ideas? Yes. Okay, a Zener diode. Well, we haven't talked about Zener diodes yet. You could do that. Just a Zener diode actually wouldn't be quite good enough, right? We need another, yes?
Or you can put two resistors in series, and one is 3 ohm and the other is 15 ohm, and then you put the V naught with the parallel with the brick one.
Perfect. So one thing is you could use 2 resistors in series. Actually, do we have a name for a circuit that puts these 2 resistors in series to the new voltage? Yeah, it's a voltage divider. So first idea is we just use a voltage divider. Hey, that's something that we just talked about. So here is this first design. So I've drawn a voltage divider now for a clever circuit, and I already picked one of the resistors. I picked 5K ohms. So now you have two ways, right? You have still 1 degree of freedom. You got to figure out what is that resistor R2. So you have two ways. One of them you can remember or derive the equation that V out is equal to V1 times R2. You got to be careful here. I do the R2 at the bottom on the other circuit diagram. I think I had it at the top of R1 plus R2. And then, of course, we know that this one's 3 volts at 18 volts. And this one is 3 volts. And we know already R1, that's 5K ohm. And then we can solve for R2, right? That's not very hard. So we can do that, but there is also a more clever way. So the current here is flowing through both resistors. What's the drop that we want across resistor R1? The voltage drop. Well, here we want to have 3 volts. Therefore, across R1, we need to have 15 volts, right? So the voltage drop across these resistors, of course, proportional. So if across the 5K ohm resistors we have a drop of 15 volts, and now across R2 we want a drop of only just 3 volts or 5 times less, well then R2 has to be 5 times less also, so it's got to be 1K ohm. And that's probably a quicker and certainly for me more pleasing way to do that, because I would have messed up this anyways if I tried to do this for you now. Okay, so we need 1K ohm. So there is a problem with this solution now. What's the problem? Actually, this wouldn't work in practice. Probably it wouldn't work. In most situations, it really wouldn't work. Why not? Yeah.
That solution assumes there's no current going through.
Exactly. We made an assumption here. We made an assumption that's probably not very practical at all. What's our assumption? Well, you just said it. We assumed that this current is 0. Well, that probably is not a reasonable assumption because, hey, you know, we built the whole thing to actually deliver some power to the load, right? So we need to somehow come up with a different solution. Well, how could you fix this problem? Well, here is a little bit of insight. So just to understand better what's going. So before we assumed that current Ix was always 0. And we just said, hey, you know, sorry, that was just a bad assumption. It was okay for a first idea, but it's a bad assumption. Now, if that's not true, what's going to happen? Well, if we start cranking up the current Ix, then the voltage across that current Ix is going to flow through which resistor? Well, it's going to flow through R1, right? So then the voltage drop across R1, of course, it's going to increase, right? We're going to drop more and more voltage across R1. Why? Well, because this voltage here is going to increase because the current Ix and therefore the current through R1 is increasing. Ohm's law again, okay? So consequently, the voltage V out actually is going to decrease. So what's going to happen is that we start out at the right voltage, 3 volts here, okay? But then, as this current Ix increases, the voltage V out is going to, as Ix increases, the voltage V out is going to decrease. Well, now, hey, we are engineers, right? Perfect is not for engineers. Engineers, we always solve the problem. We do something that is good enough. It doesn't come short of the requirement. Of course not, right? Otherwise, we don't meet requirements. We get a lot of problems, right? But we're not going to over-design. Yes, you have a question?
Do you have a specific resistance for the component we're trying to push the volts for?
Well, maybe we could cast it in that way, but probably a better way to think about that component, X1 or whatever, XL, the load, right, is that, you know, it draws a current, and we can probably look that up in a data sheet or so. It draws a current that is anywhere from, for example, 0 amps and could increase to as much as Pick a number. Let's pick 100 milliamps, okay? So the current through this component can be anything from 0 to 100 milliamps, okay? Now, of course, that corresponds to a resistor. The resistor all the way here, the corresponding resistance all the way here would be infinite, right? No currents flowing, open circuit. And here there's some other number, right? Okay. And then we need to also figure out something from the data sheet. We need to figure out what is the minimum voltage this thing still runs off, right? Any circuit that we design that runs off 3 volts, and if the voltage is 1 microvolt too big, it's going to blow up. And if it's 1 microvolt too little, it's going to stop working. Well, that really would be a totally impractical, useless circuit. So in practice, every circuit will accept a certain tolerance, and you need to look that up in the data sheet, what it is. So for our example, we assume that the component actually works for a voltage as low as 2.5 volts and as high as 3 volts. And the current is going to vary between 0 volts and 100 milliamps. Now, I already kind of drew how we are going to design our power supply or so here. I said, well, gee, you know, when no current is flowing, the voltage is highest, and the highest voltage that our component tolerates is 3 volts. Consequently, that's what we pick for a current 0. And then, as the current gets to its maximum, well, the voltage is going to be at its minimum. The voltage that comes out of our supply is going to be at its minimum, and the component tolerates a minimum of 2.5 volts. And so that's the characteristic that we're going to design for our thing. Okay? So now we have a more practical goal. We want to build a supply that follows this red line there, those characteristics. And now, again, we have to go back and use Kirchhoff's laws and so on to figure out what is the voltage V out as a function of Ix. And of course, it also depends on the resistors R1 and R2. Those resistors are unknown, but we're going to figure those out. Actually, we're not going to use 5K ohm. And of course, it also depends on V1, but that one, fortunately, is given. So now we have to use Kirchhoff's laws and Ohm's law and so on to figure out this relationship here. Well, let's go and try to do this. So let's go and try to write an equation for V out. So V out, that's the voltage across this component XL, and it's also, of course, the voltage across our resistor R2. Why? Well, we could figure out that very easily from Kirchhoff's voltage law. We can also just see that these components are in parallel, so the voltage is the same across each of them. All right, so now could we write an equation for that V out? Well, let's try an equation. What else do we know? Well, we actually know what is V1. Well, the voltage V out, which is the voltage here also, is going to be equal to the voltage V1 minus the voltage, let's call this Vy or so. Again, we can give it. So what is Vi? Well, Vi is going to be equal to the current that's flowing there, I1, I have that at the top, times the value of the resistor, R1. Okay? That's certainly an okay equation, right? Now, there is one little problem in this equation. What's the problem in this equation? Well, we multiply with I1, right? And we don't know what is I1, so we need another equation. I1 is equal to, well, I1 is really equal to I2. I2 you see here, plus Ix. And what is I2? Well, I2 is equal to V0 divided by R2, right? Plus Ix. Then we go and substitute this up here. And what we get is, and solve and so on, and then we get V out is equal to R2 over R1 plus R2 times V1 minus R2 Ix. And of course, I wrote this somewhere in the corner of my cheat sheet, so that's how I could do this so quickly. But obviously, I expect you that it will take you a little bit while, right? So after a while, you get the hang of it, and you will see what kind of equations can I write. Actually, there's one thing that is nice about Kirchhoff's laws. There is an almost infinite supply of equations that we can write about our circuit. What's the problem if we write an almost infinite number of equations? They're going to be linear dependent on each other, and then we work very hard, and at the end we know that 5 equals 5 or something like that, right? So that's really kind of the problem about Kirchhoff's laws. We are not short on the supply of equations. We can write equations. The trouble is we have to develop a little bit of insight on writing the right equations so that you don't get a trivial result, but actually what we want to know. So once we have the equations, then you take math, whatever it is, 1A or so, and you use your math skills, and you actually solve the problem. So that's not a topic of 40. I just assume that you know how to deal with that. Usually we will have situations like this one where we have 2 equations, 2 unknowns. Occasionally we'll have 3 equations and 3 unknowns. Okay? Also, sometimes there's a clever way to write a circuit and you get only 1 equation right away. And there is another not so clever way, and you end up with 4 equations, right? So that of course is also that you have to solve. All right, so now there is one more thing that we need to do. Now we know that, let me use another color here. We know that when V out is 0 volts, we know that Ix, or for Ix, V out is 3 volts. For Ix equals 0 milliamps, right? And we know that V out, 2.5 volts, corresponds to Ix equals 100 millivolts. Okay? So we, milliamps, thank you. So we can use this now and plug these values into the equation that we just derived. Okay? And then we get 2 equations, because we have 2 conditions. We get 2 equations, and these equations have how many unknowns? 2, which are R1 and R2, right? And then, of course, we can solve for R1 and R2. And once we solve for R1 and R2, well, we have solved our problem. And did I write what R? No, I didn't write it. Oh, yeah, R1, I did write it for me already. I did solve it. You can try it yourselves and see whether you get the same thing or whether I made a mistake. 150 ohms, and R2 is 30 ohms. Okay? So now we actually solve the problem. But whenever we solve a problem, what should we do at the end? Yeah, we should first of all, of course, verify whether the solution is correct. Let's assume that I'll let you do that. And then there is one other thing. We should look at, is this solution really so great? So here we just look a little bit at what's really happening with the solution. So here actually I put even the value of the resistors. But what I also put in is what we really want to do right here. So we have a source V1. That source, the point of the source in this application is that it delivers power, right? That's why we have it there. And so that's the big blue fat arrow. That's the power that source delivers. And then, why actually does it deliver power? Well, because we have a load here, and that dissipates power. That's the green arrow, okay? Now, obviously, in a well-designed circuit, all of the power from the source, so all the blue stuff, goes into the green one, right? That's really what we want, right? Now, unfortunately, that's not what's happening in this circuit. The circuit will work fine. It will meet all the requirements, unless I made a goof in calculating the resistor values. But unfortunately, there are these 2 resistors there, and they're going to dissipate power also. They're going to dissipate power P1, and they're going to dissipate power P2, right? And that really shouldn't happen. Now, at this point, we really don't know a way on how to get around that, because with resistors, hey, you know, you can only build circuits that dissipate power. You can build useful stuff, but, you know, it has something. So now we could quantify how good this circuit is, and we could quantify this with an efficiency, right? The efficiency should be 100% if all the power, all the blue stuff goes into the green one, right? That's what we want. And the efficiency is going to be less than 100% if there is some power that ends up here. And if all the power ends up there, well, then the efficiency is 0%. So I use the PL, that's the power that's actually dissipating a load. Maybe that's not great either if the load dissipates power, but, you know, if we want something, we got to put in something for it. You want a salary too, once you're great engineers after EE40, right? And then what is PS? Well, PS is the power that's delivered by the source, so that's the blue guy. Okay? And of course, they are related to the red ones. PL, for example, would be equal PS minus P1 minus P2. What are P1 and P2? Well, we can figure that out using Kirchhoff's laws and Ohm's law and so on, and I'll leave that for you as an exercise. But we can now plug in some numbers, and actually I did that here. For example, if Ix is 0, what's PL gonna be? It's gonna be 0, right? What's PS gonna be? It's exactly, it's something more than 0 because there is current running just through the voltage divider, right? And so the efficiency in that case, I don't even need to know what is P1 and P2, but the efficiency is going to be 0%. So at the other end, if Ix is 100 milliamps, then we actually know is 2.5 volts because that's how we designed the circuit. And now we actually need to calculate what P1 and P2 is, and I did that. And again, I put the number here, so you can go home and try it also and see whether you get the same number. I'll give you $20 if I made an error. Only the first one, otherwise I'll go bankrupt. I'm sure there are plenty. So then there is 13.4%. Is this a good efficiency? It's terrible, right? What would be a good efficiency?
80%.
Yeah, okay, so a really good, perfect efficiency, of course, would be 100%, but yes. 80% or so is it's kind of practical. It's kind of practical. Maybe you can get a little bit over 80%, 90% or so if you build it right. But nobody knows how to build this with 100% efficiency or so. Whatever clever stuff you put in here, it's going to dissipate some power, but not 95% or 96% of the total. Yeah?
Is it nobody knows, or is it like proved impossible?
Actually, I guess you could. Yeah, I guess you could prove it easily that it's impossible because something has to happen here, and how could you make this without there here being any dissipation whatsoever? Probably. But anyways, I mean, later in the course, actually this is kind of a motivator because later in the course we'll design a circuit that does this, and it gets an efficiency that is 90% or so. Okay, but we will need components in addition to these resistors. Okay? But resistors, nevertheless, resistors are very useful circuits, and on Monday maybe we can even start a little bit today. We're going to look at the design example that, hey, you know, people make a career out of just resistors, and a very nice career for that matter. Okay, but before that, let's figure out what's going to be on the test, right? Okay, so and also what I consider to be really important and useful. So, well, we have seen IV diagrams. I would like, hey, that's really a trivial stuff, right? I would like you to be able to either draw an IV diagram for components. We'll do that in the laboratory, or alternatively, of course, you should be able, and my kids in grade school can do that too, so I'm sure you will be, if you have any characteristic here, maybe linear, maybe even not linear, you can figure out, well, if the current has one value, the voltage has another one. Obviously, right? So Then, in particular, you need to know about ideal sources and resistors. You need to know their characteristics and represent them graphically. That again means that you know how to draw the IV diagrams for these components. That's already getting a little bit tricky. You know that for doctoral students here, perhaps, you know, we have this exam called prelim, and typical first question is, hey, you know, draw me the IV characteristic for, usually use a transistor, not the resistor, but nevertheless, and you know, 20% of students don't know how to do this, so pay attention for it. It will help you on your prelim exam if you choose to pass that. And then, of course, also analytically, what would be the analytical description of a voltage source? Yeah, how would you describe a voltage source analytically? The voltage across it would have some set value, and the current? Exactly. You can do that also for the current source, and you can do that for the resistor, and if you do it for the resistor, then that thing has a name, which is Ohm's law, right? Exactly. So I expect that you can do that. Okay, so then this is a little bit open here, and we will do lots of examples, and we learn better techniques also for this, but if you have a circuit with ideal sources and resistors, you can use these laws that we just talked about, and you can use Kirchhoff's laws. So now you got to put things together, and you can figure out the voltages and the unknown voltages and unknown currents in that circuit. We did that just in the example before, and we'll do it many, many more times. So that's a skill that I understand. We are sort of just at the beginning, but it will develop more and more, and that's important. You need to know that. You need to recognize, you need to know, first of all, what is parallel, what is series connection. You need to recognize those, and then you need to apply appropriate laws, in particular for resistors, right? We know how to simplify resistive circuits if we have resistors that are either in parallel or in series or combinations thereof. Represent a network of many resistors with a single resistor. Well, we did an example or two for that. Again, that's the series parallel kind of business, and we'll do that frequently. And you just need to know that. If you can do that by spending 10 minutes thinking about it, that's great. You have basically understood it. But now you need to develop the skills so that you can do it in 5 seconds. Okay? Recognize divider circuits and determine voltages and currents. What kind of dividers do we have? Voltage divider and current divider. Voltage divider, the components or the resistors are in series, and for the current divider, they would be in parallel. You need to recognize these things, and then you need to be able to analyze them in the blink of a second. Again, if you can do that in 10 minutes, and we have a quiz or even an exam, you will say that, oh, this was terribly long, and I didn't have enough time to do it. All you will get from me is sorry. Okay? Yes?
Can we assume the problems on the exam are similar to the quizzes?
No, the problems on the exams, they will be harder than the problems on the quizzes. So I posted a sample quiz on the web. You can look at those problems. They are designed such that, hey, you know, if you followed the class, if you understood what's going on. So, for example, on Monday, we could have one of these quiz problems, and there would be a voltage divider, and I would expect that you can apply, that you understand that now. But on the exam, we will do harder stuff, more like the last example that we just went over, right? This thing here, this kind of thing would be more. Obviously, there is going to be sample exams on the web also, well in advance of the actual exam. They will be these exams. The exam questions are going to be more like the homework problems. Although sometimes in homework I give harder problems than I would in the exam. Make sense? All right. Have a nice weekend. Again, we only have weekend here.